Hello everyone and welcome to ML Done and to the second video of coding your binary classification from scratch, binary classifier from scratch using pure NumPy. Just a quick review as to what we talked about the last time. So let me get rid of this. Yeah. So this is the neural network that we decided to implement. So we said that our input data is one-dimensional. We have one bias unit over here, x0, and we got two weights, w0, w1, and then z is the linear combination of your inputs. And then we have the nonlinearity sigmoid that will be applied on z, would squash it between 0 and 1. And then y hat, or sigmoid of z, would be the ultimate output of your perceptron. And then we said that because we are developing a binary classifier, we are going to use the binary cross entropy function. So today in this video, we're going to pick up where we left off. So in the previous session, we came up right up to this point where we defined the parameters of our neural network. So we generated W0 and W1 as NumPy arrays that have just one value. We defined the number of epochs as 200 and the learning rate 1,000th. And we said that an epoch is actually one sweep throughout the whole training set. So this is not a neural network course. This is mainly going to focus on the coding aspect of this. But and so generally in training neural networks, what happens is that you would go through your training data multiple times, and every time you would shuffle up your training data, okay? And you're hoping that introducing this randomness would result in a better machine learning algorithm. So today we're gonna start from that point, but before that, let me just go through the math that we discussed the last time. So you can see z, y hat, and your binary cross entropy error function. So this was the error function that we have already implemented. Y is the ground truth, y hat is the prediction of your network, which is the ultimate output. This is how we implemented it. Again, this is the post that is related to this particular video. You'll find the whole code in this blog post at mldone.com. And here's the part where we implemented the basically the gradient of the error with respect to y hat and the gradient of y hat with respect to z, meaning that if you look at here, y hat, which is the output of your sigmoid, with respect to the input of the sigmoid, which is z. And we said that that is actually equal to y hat multiplied by 1 minus y hat, or sigmoid of z multiplied by 1 minus the sigmoid of z. And then we implemented these two functions that are responsible solely on computing these two derivatives. And we said that we're going to use these derivatives to actually implement a backpropagation algorithm using chain rule and basically moving towards finalizing the whole code on building our classifier. Now, before I move on, I just want to show you something before I start coding. So if you look at this diagram over here, z is a function of your inputs, linearly combined by the weights. Y hat is a function of z, and error is the function of y hat. So we have this idea of nested functions on top of each other, right? So let me just show you something. So when you think about the error and you want to find the learning route for updating your parameters, in this example, the parameters are w1 and w0, the coefficients of the linear combination of your inputs, right? So if you think about it, the derivative of error with respect to, say, w1, okay? Using the chain rule, even though error, excuse me, even though your error is not a direct function of your w1, but error is an immediate function of your y hat. So you got the derivative of error with respect to y hat. And interesting enough, your y hat is a direct function of z. And then z is a direct function of your parameter w1. The same story about w0. You get e derivative with respect to w0. Again, e is a function of y hat, so you can say derivative error with respect to your y hat. And then y hat is a direct function of z, so you can just say derivative of y hat with respect to z. And then z is a function of w1 and w0, so you can just say the derivative of z with respect to w0. All of this is possible because of this thing called the chain rule. Now, in plain English, what does this mean? It means the rate of change in your ultimate error with respect to this particular parameter w1 has something to do with three elements multiplied by each other. The first element is the rate of change of your error with respect to y hat, meaning that if I increase y hat or decrease y hat, how much will error change? The second one is y hat with respect to z, the rate of change of your y hat, the output of your sigmoid with respect to the input of your sigmoid. And finally, z is a function of w1. So what is the rate of change of z with respect to w1? So if you multiply them together, according to this beautiful and sort of intuitive rule called the chain rule, you will actually get the ultimate derivative, which is the derivative of error with respect to w1. The same story goes with a derivative of your error with respect to w0. Yeah. Now, after you computed these, then you would say your w1, the new w1, is equal to the old value of your w1, always minus the learning rate, which is just a step size, multiplied by the rate of change of your error with respect to that w1. And same story goes with w0. w0 new is equal to w0 old minus the learning rate of the error with respect to w0. So these two are called the learning rules, and they use the chain rule over here. Okay. Again, this is not a neural network course, otherwise I would have really focused on why do we always subtract this second term from the first term. It is because we always move to the opposite direction of the derivative. Okay, so if the rate of change of error with respect to w1 is a positive value, it means if I increase my w, your error will also increase, right? So this is a positive value. So it means you have to decrease your w so that your error would decrease as well, because remember, the ultimate goal is to minimize the error. So when the rate of change is positive, you are saying minus that value. So you're reducing your w. Now, if the rate of change is negative, what does that mean? It means if you increase your w, then your error will decrease. So this means that when the error, the derivative of the error with respect to your w is negative, it means that you have to increase your w in order to be able to decrease your error. So I think it's not a bad idea to actually explain this a little bit more. So if you think about it, let's say you've got your error. This is a very simple example. You've got your error with respect to, let's say you have just one parameter, w, and this is your error. And let's say the behavior of your error with respect to your w is something like this, right? And then let's say you take the derivative of your error with respect to your w at a given point. Let's call it w0 over here, or let's just say wi. Okay, and if you think about it, if you see where does this touch your plot, it touches over here. What does the derivative of error with respect to w really mean? It's the rate of change or the slope of the tangent line. Okay? It means this is sort of the tangent line on your error surface at this point, and the slope is positive. Now, if this was the point at which we wanted to take the derivative of your error with respect to, say, wj over here, this would have touched the plot over here, and the slope of tangent would be like this. And here, the slope is negative. What does this mean? Let's first talk about the case where s is bigger than 0. This means that the rate of change of your error with respect to your w is positive. It means the relationships are towards the same direction. It means if you increase your w, right here, if you increase your w at this point, at point wi, if you start increasing your w epsilon amount, your error will also increase. And in the second case, when the slope is negative, it means the rate of change of your error with respect to your w is negative. So how should I decrease my my error? It means if I increase my w, then my error will go down. Think about it, wj over here. If I go a little bit to right, the error would be at this point then. Like, let's say epsilon, at this point of w. The error will go from this point to this point. So your error will decrease. So as you can see, in order to, in the first case, in order to decrease your error, you have to decrease your w. This is the case where the rate of change of your error with respect to w was positive. And in the second case, you say that I have to increase my w so that my error will go down. And that is the case where the derivative of the error with respect to w is actually negative. So what can you understand from this? This means one and only one thing. It means the direction of parameter update is the opposite of the direction of what? Of the gradient of gradient. So that is why in here we have these minus values. So we always say whatever the sign of the derivative of error with respect to my parameter is, I'm always going to go to the opposite direction. Okay? So if that value was positive, I'm going to make sure that I'm going to say minus that positive value. So W1 old will be subtracted, will become less. That means you're reducing your W. And in the second case, when the derivative of your error with respect to your W0 is negative, you're saying that minus that negative number, which will be minus multiplied by minus, will become a positive value. So you're actually increasing your W. So W old will be plus a value. That is because we said that over here, when over here in this case, when that value, the derivative value is negative, in order to decrease your error, you need to actually increase your W. And that is the only way you can minimize your error. So, so in this video, it was going to be mostly about this science of backpropagation, the chain rule, and how you can actually update the parameters. In the next video, we're gonna actually officially start coding this, but this was really important for you to understand. In the next video, you're gonna see how we will implement each one of these derivatives. So we have already implemented this term and we have implemented this term. The third term, we still haven't touched it. So you're going to see how we can implement each one of these derivatives, and we multiply them together to to compute the derivative of error with respect to the parameter. And then you will see how we implement these two learning rules to update our weights, which is basically learning the weights. So I'm going to post again the link to this blog post into the description of this video. I hope that this has been informative for you. See you in the next time, which we're gonna actually dig in much more into the coding of this perceptron to develop our binary classifier. So until then, on behalf of Ameldan, take care of yourselves. Bye-bye.